Welcome to 1,000 Cuts Down to 5, how to keep Unity's drawcalls and other bottlenecks in check. This is a case study and a list of the lessons I learned developing for a platform that literally burst into flames on people's faces. I'm CrateSmith, or also Kieron Lord. Now, I have to have a disclaimer for all my talks. I swear a lot when I'm doing talks, I rant a lot, so that's all right. And this was a really hard talk to make. This is probably the hardest talk I've ever had to do because there's so much detail, but there's actually a very non-technical angle to this talk, which is the main point. So there was going to be 5 really critical steps to getting to this, and then after about the 8th rewrite, it didn't make any sense for the title anymore. So let's go and do the real title. Optimization takes your entire team. How to actually keep performance in check. By, this guy who sucks at naming talks. There's a little mouse cursor that's annoying me. Oh, I'm gonna have to live with it. Okay, so about me. I guess a lot of people here know me, but I make games, which is not really surprising. I've made these fine games, and as you can see, I've worked on a whole lot of different platforms and different sorts of things, and I even did like consulting and professional education, and like I was in a company where we taught people about how to do AI, AAA companies how to do AI better. But the main thing this talk is about is lessons learned on those bottom 3 games, and specifically the bottom one, and how we got that all working on device in correct frame rate. So, first of all, what this talk isn't. This is not a deep dive into a particular piece of hardware or how to optimize a particular kind of game. We will touch on a lot of stuff that you have in a talk that was that, but I'm not going to have any hard limits on don't use this feature, don't have more than this number of draw calls in your game, like none of that stuff. This talk is really a case study about a project that was nightmarishly hard to optimize, like a platform that was just really, really hard to work with, and the process that we used to actually develop a game for it. This is a process and workflow talk, not a traditional optimization talk. So, because of that, let's start by talking about philosophy. The first point about anything you make is that it has to be shippable. Now, there's an exclusion here. If it's a prototype or a first pass, that's okay, that's fair. But anytime you're going to tick off something and say, this is done, you've got to be ready to say that like this is okay if it goes into the final game. And performance is a major part of that quality, that thing being done. If performance is bad, what's going to happen is that work's going to need to be redone or crunched or cut, or something else is going to need to be in its place. So that's the first step. The second one is a concept of baseline optimization. You need baseline performance at all times in order to make your game. If your game is not running at the target frame rate, you aren't developing the game how it's going to feel. So basically, a designer who's running the game and developing content for it when it's running half its normal frame rate is not getting the game feel for the final game. So they're developing with the wrong target. Now, there is this phrase that goes around that says, early optimization is the root of all evil. And I really don't like it because people take it as gospel. They essentially say, oh, don't do this because the saying says this. Deep optimization is a major problem, and that's what that saying is speaking to. However, if your game is running under the frame rate, that is an actual bug. It's like your game is currently not doing what it's supposed to. You need to fix it. And worse still, this phrase encourages people to leave optimization to last. Like, we'll fix up the optimization when we get into the polish phases. No. It's like adding audio at the end. It's just a terrible idea. It's like you're not going to be guaranteed to be able to pull it off. So, yeah, just don't do this. Finally, and possibly most importantly, everyone on the team needs to be as independent as possible, and performance is everybody's responsibility. Everyone on the team needs the tools and knowledge to manage performance in the things they're working on. And you, regardless of your role on the team, like it sounds like I'm just talking to programmers here. No, everyone needs to make tools and teach the other members of the team how to work with them, how to interface between the different roles so that people aren't creating downtime or being forced to wait for somebody else's help just to do their basic stuff. If there's a performance problem, a common error or busy work that can be automated as part of your workflow, it doesn't matter if you're a programmer or anyone else. Do it. Try and figure out a way to just cut down and just have pure iteration time. And this is actually an example here. We had a major problem with our art assets in this game. During one phase of development, there was a problem. It was going to be hundreds of hours of artist work to fix it up. All busy work, no new content. It took a programmer 5 minutes to make a tool that corrected all the problems. So, like, when something's an art problem, often there's a programming tool that can solve it and so forth. It's just keep everyone working on their own content. So, let's just get cracking on this thing and talk about the game and the platform and get into the nightmare. The game was Zombie Nom Nom, and you'll be forgiven for not knowing about it because it did not sell very well. It's a first-person walking game. You always move forward, so it's a VR game where you stand on the spot and it will just walk in whichever direction you look in, and you're a zombie, you run into people and you eat their brains. And the round ends if you don't eat brains for a certain amount of time, and there's lots of power-ups and combo systems and etc. But the main point was, so it was a fun little dumb game. You look really dumb while you're playing it, and all your friends laugh at you, and that's the general point. From a technical angle, we had very small environments, very complex ones visually, well, by GearVR standards. And here's the GearVR. This is a positively anemic piece of hardware. I do not want to work on it again. Here, after 3 games, these are the rough guidelines that we learned to develop for it. You've got about 75,000 tries that you can use for environments or static geometry, 8,000 tries for any dynamic stuff. You've got to keep it under about 25 drawcalls per eye. The older devices don't support instancing, so the newer ones can actually get away with more, but the older ones, which you still want to support, need to be hitting that required 60 frames per second, and oh my god, no. So yeah, that's the stereo single pass rendering thing is really useful, but it's only supported by some of them. And then the kicker is that the Note 7 model can explode. Literally. Which is not good for sales. So, programming guidelines. We were at the start of this project and we needed to make sure that we weren't killing ourselves by writing stuff that wasn't not fit for task. So the first goal was, we only want to write code that's quick and easy to edit and has a good baseline performance. We're not going to dig in deep and try and solve things so they run perfectly. That's where we go in and profile everything. You profile everything before and after you make a change and figure out how much you lost and what happened. And then refactor areas that are running slow. Like optimize the stuff you need to optimize, but don't just go optimizing willy-nilly. Find an area that's a problem and work on that. And then focus on shortcuts rather than trying to solve your way through major issues, which wasn't always available. So the profiler. And this is going to be a bit of contention. Everyone on the project should know how to use the profiler. Artists, level designers, they don't need to know all of it, but there are parts of that that's relevant to everybody. But first, for now, let's just talk about the programmer. The programmer needs to be able to test everything with the profiler before it's put into the game. Like, check beforehand, check if you're creating any allocations on the heap, just make sure that you're not putting anything in that's actually broken in some way, even if it's some small way. And never, ever rely on your gut feel. Like, if you spend 2 hours working on something, you're going to think it's faster, even if it's slower. Always check before and after that you're actually getting a better frame rate and the thing you're working on is either not too expensive or not more expensive than what it's replacing. Tools and automation. As a programmer, you are not just responsible for creating your own features, you are responsible for the workflow efficiency of everybody else on the team. If somebody in a non-technical role is spending a lot of time doing technical busy work, that's a key area that you can possibly speed up. And don't just use Unity's internal features. Like the main thing about Unity, the main awesome thing about it that I wish other engines would support is just how much you can make it into your own editor. Like turn Unity into the editor for your game, don't use it as a sort of a default editor. Next, little show of hands. How many people in here have got accurate benchmarked limits for how many characters they can have at any time in their game, like how many polys can be on screen, just those two. Okay. I was hoping for a lot more. This is incredibly important. We'll get to this a bit later, but having these limits and knowing these limits gives you, it essentially gives the rest of the team the ability to know what's going on with the project, and they can help you optimize the project. So even from the like as soon as you got a prototype, you can just stress test the game. What happens when we have 100 characters? What we have, like, where's that limit where performance starts to break down? And then always give yourself a breathing room, like a certain amount of headroom between the actual limit and what you set the sort of target as, just so that exceptional cases can be allowed, and also if something has to go over, it doesn't break performance. So, and then let's just quickly go over some of the problem areas that programmers will have to face. I won't go into detail onto how to solve these things because there are really good resources that should be entire talks unto themselves, but they're things we need to cover. First of all, garbage collection. Garbage collection and heap allocation is very slow. Fortunately, it's a programming only problem. Programmers create it and programmers fix it, and everyone else in the team doesn't need to know a thing about it. The big important thing to take away from this is the PC and editor versions of your game are not nearly as badly affected as consoles and VR headsets, mobile, etc. Basically, every platform has a different amount of severity to this problem, and if you're trying to port your game and you've left garbage collection in there, and it's running okay on PC, it probably won't run well on console at all, and you'll need to spend a huge amount of time sorting that out. So the reason that garbage collection is so bad is that the actual performance problem is caused by the heap becoming full or fragmented or just too much time having passed since the last done a cleanup. When it does a cleanup, it actually goes through and really gets rid of all those objects that you've deleted and stopped using. That's a massive spike. It's not an efficient process. So the best you can do is to manage the severity of the spike by manually triggering the garbage collection yourself. But beyond that, your only real recourse is to try and minimize all the allocations you can and reuse as much memory as you can. So the most important thing is get all programmers on your team, to read the official Optimizing Garbage Collection in Unity tutorial. It's on their website, it's incredibly detailed, and if I went through everything in there, this talk would be 4 hours long. In brief, the main topics are avoiding functions that return any kind of new object. Make sure everyone on your project understands the rules around boxing. Boxing is a very insidious and easily hidden problem. It appears in, you can't actually see it easily in normal code, but it creates a lot of garbage. Avoid link like the plague, unless you're actually checking the IL that it's generating from your code, because it's so easy for it to generate boxing in ways that you won't be able to find. And then pull and reuse any allocations you possibly can. Okay, so other areas, physics complexity. Try to keep your environments as simple as possible. The cost per raycast and per collider is actually just relative to the amount of other things around them that they need to test against. So using layer masks can cut things down. Keeping the environment clean is another thing. And this seems like stuff for level designers and other people on the team, but you can design the code for the game so that it needs to use a lot less of these, or have a much more simple environment to work with. And then finally, the gold rule for optimization isn't to do the same amount of work faster. It's to do less work. If you have something in update that doesn't really need to be done, like half of your update function could be done every second or occasionally at a variable rate depending on how far away it is from the player, break that out into a separate coroutine, or put it on make a manager for it that round robin updates the objects one at a time, maybe does 2 objects per frame. It's a really easy way to save an enormous amount of time. If you're running AI on every single character, every single frame, it's just going to murder the CPU. So these mostly worked really well. Their biggest saving was having everyone test everything in the profile before and after a change, meant that we were actually abreast of what was happening at all times with regards to performance. Getting everyone on board with garbage collection allocation rules in boxing was a time investment that paid off. And yeah, benchmark your game. Like, we'll get onto how it's useful soon, but holy crap, it actually means that you can share the load of optimizing your game. Okay, so the rendering pipeline. This is the weird part of the talk because it actually doesn't feel like it belongs in this talk, but in order to describe what's important later in the talk, we have to cover some of these things. The biggest problem was the core gameplay of this game was really pushing the limits of what the GearVR could render. Most people making GearVR games make them focused on a static viewpoint and then optimize static geometry for everything, very little dynamic geometry and very few effects and things like that. We were having one where you could walk around, view anything you wanted from any direction. We were really pushing it in a direction they really didn't intend for. So, the first thing is batching and draw calls. Show of hands, how familiar is everyone with this topic? Is everyone confident? Good, okay, we can blaze through this detail quickly. But basically, the long and short of draw calls is that just understand that draw calls are a CPU cost that occurs on the render thread for it to feed information to the GPU. So if the GPU is too busy, the render thread gets delayed waiting for it to become ready, but you can be CPU bound on the render thread when you've got too many draw calls. Now, PC draw calls are generally less expensive, but platforms like the GearVR, and it's platform specific how expensive this is on the CPU because it all comes down to drivers. The good news is these new rendering APIs. I couldn't actually find a new DirectX logo that worked well in black. The API you use has a catastrophic effect on draw call performance, at least as far as the CPU is concerned. These new ones like Vulkan, Metal, DirectX 12 have support for seriously multi-threaded draw call submission. And as a result, the CPU cost of actually submitting stuff to the graphics card is eradicated. So always benchmark how much you're actually paying on these things. Batching may not be a major thing for your game if you're only supporting platforms that support these features. So always benchmark. But in our case, we were very dependent on batching. So static batching is the first one. Under the hood, static batching works by essentially creating different sets of pre-baked geometry and renders them based on what you can currently see. As a result, it has a pretty significant memory overhead. You can actually bake them at runtime. There's an API for that, but it has quite a bit of it will stall your game pretty hard. It is a very efficient system. It reliably saves you CPU time on draw calls, but it does eat up a bit of memory. However, it's not that good at doing lots and lots and lots of tiny objects. If you can feed it a bunch of big objects, it's much better at cutting down the amount of time, because before it operates, every single one of the objects needs to be frustum culled and decided which set it's going to work with. So it works so much more efficiently if you've got like 10 big objects as opposed to 100 tiny ones. Dynamic batching. Okay, word of warning. Dynamic batching is so bad that Unity is looking at ripping it out of the engine. It works by merging groups of small meshes into a single mesh on the CPU every frame before rendering it. It's limited in size to roughly 300. It's kind of a magic system that's all a bit bullshit. And it only ever saves CPU on platforms where the draw call cost is just terrifyingly bad, like the GearVR. But also some mobile platforms, like say you've got a release on an iPhone 4. That's the sort of thing this is good for. Whenever you're looking at your project, test with and without dynamic batching, like just on and off, and see if it actually gives you a saving. If you're on any kind of hardware that's reasonably new, you're probably just going to see that it's a net loss. It'll cut down the draw calls, but the actual render thread will run much, much worse. Instancing. I wish we could use instancing on this game. It works differently from other batching. It lets you render multiple copies of the same mesh with different render parameters, so you can easily have 200 versions of the same mesh, all with different colors or different shader parameters. You can get really fancy and actually do GPU animation and have everything animated individually. So if you've ever seen those demos where they've got 100,000 little soldiers running around, that's one object, and then they've got shader parameters for the animation. This would have been perfect for our game, but it wasn't supported for the GearVR at the time. So sadly, I don't have a lot more I can say about it than that. What we did have was the worst case scenario. We had crowds of characters because there needed to be enough people to eat. Lots and lots of dynamic objects, all those power-ups and various other things in the scene. Very high draw call cost. This is just something about the hardware and the fact that it was mobile VR. And instancing wasn't supported, so we had to rely entirely on static and dynamic batching. That meant that all of our assets need to be authored and processed and combined to make maximum use of these two batching types. That meant that we had to use atlasing for everything. Everything needed to use the minimum number of textures, and we were constantly alternating between the GPU locking us out and being CPU bound on too many draw calls. So there was a constant balancing act for that at all times. Sorry about that. So the next one is, what did we do about that? We basically had to go back to the profiler. Whenever we saw a problem, we had to double check, are we CPU bound or are we GPU bound? In this case here, you can see little GFX wait for commands on the screen. Unfortunately, I think the text is a bit small. So that's a moment when the render thread, which is this area down here, that's basically the main area you want to look at when you're looking at how much you're actually paying on draw calls. We can see that it spends a fair amount of time with that wait for commands. And that's when the GPU is essentially too busy to receive more commands. And then after that, we've got a long process, which is camera.render, and that's literally just draw calls are happening. If you expand the window out further, you'll get more detail on is it doing opaque or transparent geometry, but camera.render is generally that block. We did run into the problem that the profiler seriously impacts performance when it's attached to the device. So much so that we had to use it as a guide and then have like a frame rate info warning that appeared in the corner of the screen if the game ran over, like dropped below frame rate. But generally it's representative, so even if it drops the frame rate in half, the values are more or less accurate. Okay, so you know you're CPU bound. You then go to the frame debugger. This is the most amazing feature that Unity has added in the last couple of years. Basically, it lets you go through and see exactly what Unity's rendering at every single stage and it will even tell you why each draw call is or isn't being batched with the one below it. It made tracking down batching issues so much easier, but that's not the only thing. It really helped us with overdraw. So one of the really big things you can save on the GPU, especially a GPU that's a tile-based one, is say we drew the background first and then drew the other things over it. That meant every single pixel on the screen is getting re-rendered. And that caused basically an invalidation of each tile, which is the low-level rendering prefers to render things as few times as possible. So the closer you can get to that by using the Z buffer, the better. So this let us catch the cases where static batching was actually drawing a whole group of things together and potentially drawing stuff out of order, and we'd be getting, say, the background mixed in with the road and possibly drawing the background before the road. Unfortunately, Frame Debugger has issues with VR devices, so we mostly had to work on an editor, but I think that might have been a bug that's been fixed since. So, basically, static batching was the biggest thing we got a win out of. We were forced to use dynamic batching, and this was a major pain. That's where most of our workflow stuff had to come in. Like our art assets need to be designed around it, our atlasing system need to be designed around it, and holy crap, the takeaway from this was just, I wish we could have made something that only supported the new APIs. Cool. So now onto the meat and tech. This is the actual part of the talk. So everyone, welcome to the talk. Right, so here's where we start with the actual content pipelines. Starting with the simple one, models. Artists should just be able to build models, get them into the game, and test them. In any game, there's generally some busy work involved, but because of the amount of extra stuff with atlasing and making sure everything worked, we had a much more extreme case that we had to simplify down. We needed to make sure that when someone was working on art for the game, they were spending as little time as possible on that technical stuff and we're just getting content iterations. So, profiler. Yes, we had to teach all the artists on the project how to use the profiler and how to check their work. So, but just the relevant stuff. So checking the number of draw calls, checking the number of polys, being able to run around a level and check that, hey, is this thing batching okay? It should be batching, but if it's not, then we need to look at that. Please do this. It's really not too complicated. Your artists really can grok how the profiler works because it's just telling them the stuff that they already see in modeling tools. Secondly, we made it so everyone could test content in the game in really easy ways. So the core of this was everything had a simple asset type. So every character had one core asset, and if, say artists wanted to go and make a new character, they just copied an existing one or created a new character type asset, for instance, filled out the different models, and then they could press play. And the idea was that you could even use the inspector for each of these specialized types to test them that have like a spawn me button up in the corner. So you load any level, hit that button a bunch of times. Like say you want to test fireman, you just select the fireman asset and hit spawn human 10 times and there's 10 firemen running around the level. Also just make it so that people can drop things into any scene and do quick tests. We'll cover that more in the build pipeline stuff, but just make it as easy as possible for them to test what they're doing and try it out in the editor, because otherwise you get them doing iterations in Max, which isn't not what the game's like. And atlasing. So we went with an automatic atlasing system. Basically, yeah, draw calls mean that you want to get everything using the smallest number of materials and textures possible. So we went and took all the source models and textures and everything and just merged them into a set of atlases based on each of the different levels. If you're interested in rolling one of these yourself, Unity provides some pretty good APIs for combining textures and getting the combined atlas, sort of UVs out for where every texture ended up in the merged one. But there's also ones on the asset store that you can pick up and that you can roll them into your pipeline. But basically, if you're working on a platform that is going to be affected by draw calls, this is a step you need to do. I'm kind of shocked that Unity doesn't support it fully out of the box. So one of the problems was that importing an atlas is not something that Unity does very quickly. And we were even doing a thing where we were pre-atlasing the models, so it was even slower. So one of the best little tricks that we had was we wrote a script that checked all of the dependencies of an object. In this case, it saved off the dependencies of our atlases and stored that. And then we could actually check, has the atlas changed? Like, have any of its input parameters changed? Have any of the assets that those input parameters are pointing to changed? This turned into a really robust solution of just saying, do we need to rebuild the generated content for this asset? And this meant that when you pushed play, it'll rebuild the atlases for the content only if necessary, literally only if the inputs have changed or the output files are missing. So this was a really big win. So yeah, like I said, auto-generating the atlases was an easier win. It's actually a lot less work than it sounds. I make it sound like I did an amazing thing, but really it was, there's a bunch of Unity functions. It's quite easy to get this stuff working. The main difficulty is just finding how to fit it into your workflow and make it work for you. Most importantly, making it work for your artists. Just having it ready and work, and when you push play, it does the things that they need it to. That's the important thing. Teaching artists to use the profiler was surprisingly easy and incredibly valuable. We're going to get on to more about that soon. There's one thing I truly regret though. One part of the pipeline that we didn't fix was exporting models and getting them to be correct. While I was doing this talk, I asked people what they did for this sort of stuff, and someone said, oh, we just let people export like a batch of models, and then we have names in the model that say, oh, this is the root of this model, and this is the root of this model, and it goes through, breaks them out into separate assets, makes sure that all their transforms are aligned correctly. It would make asset importing so much easier for the artists. We just didn't think of it. So that's something I'm definitely doing in future. But yeah, just try and minimize their workflow. Get them working on models as much as possible. The level design and environment art pipeline. This is the really, really nice one. So we did have one or two people who were dedicated towards like design and level design in the game, but most of the team worked on levels together. That's a bit strange. Oh no, sorry. Next slide. Despite the restrictions and tools and limitations, everyone had to know how to make levels because it was just that big a job making the content for this game. So we had one advantage in this. Almost everyone on the project had worked with ProBuilder before. Does everyone know what that is? Cool, yeah. Didn't even need to ask about hands. Yes, so we started and used that as a base. So we built the environments, everything was built in Greybox using ProBuilder. So visual meshes were, we built the sort of collision geometry in ProBuilder and we kept it. Then we put visual meshes over it. The visual meshes aren't used for they're not considered for the nav mesh, they're not considered for anything but occlusion culling. And this meant that we had really fast design geometry. It was much faster for physics. It worked really well on device. It meant that we had so clean nav meshes. There was no weird janky edges. It was just smooth edges, really easy, really predictable. Let's let that play out. Yeah. Next thing was saving. We didn't want people having to go through and manually go to the occlusion culling tab and bake that, and the navigation tab and bake that, and no, that's insane. So what we did was we wrote save processes that watch for when you save the scene, and then we do a ton of calculation based off what you've changed. So if you moved any colliders, what it'll do is it'll rebake the nav meshes, and occlusion culling gets changed if you've made any significant changes to the visual meshes or any ProBuilder objects marked as occluders. It also went through and tested the scene for common mistakes. Like, I'll get into what chunks are in a moment, but if any geometry wasn't in a chunk or wasn't in a culling group, we would throw warnings saying, hey, there's a thing out here that's not getting atlased, or here, there's a thing out here that's never going to get culled. So, and doing this when you save the scene is a really good time for this because that's the moment when someone's committing a bunch of different changes to the level, and people always save before they press play, or generally they develop a habit of it. So chunks. So chunks were our solution to the static batching not liking thousands and thousands of tiny objects, because our game was made of thousands and thousands of tiny objects. So it's a parent object that merges all of its child meshes into the smallest number of material groups as possible and creates a mesh for each of those. So basically, when you press play, it turns all its children into that, atlases it, and you get basically one mesh usually. And everyone was responsible for setting these up, not just the programmer, not just the environment artist. Everyone got to rebalance these. And by doing this by hand, we actually let people do trade-offs between drawcalls, polycounts, and because everyone knew what the limits were, they started being able to play with these numbers themselves. So on those limits, we benchmarked them all. There's safe limit of 75k static tries, 8k dynamic tries, 25 drawcalls per eye. Everyone knew how to read those in the profiler. And so people would move things around between chunks and then play the game and watch the profiler. And if it didn't go over those limits, or if it did, they had to resort the things, take stuff out. But if they could figure out a way to get those numbers down, then they could put more stuff in. And this was where things got amazing. 1 week after that, we had all this stuff going. Quality in every level in the game just skyrocketed. It was just, we were fitting so much more content in because everyone on the team was playing this game of, how do I get the numbers down? So we were like, oh shit, well, we're wasting polygons everywhere. So we added in other tools like bounding boxes, which just, if there's any chunk in that sector, that's basically, it's like backface culling. You put down a bounding volume, you give it a direction and a threshold angle, and any faces fully enclosed in the bounding volume that are roughly in that direction get removed or ignored during the chunking process. Generally, we cut about 20% of every level using this. There was a slight problem though, because this happens after light mapping, we still waste space in the light map for those removed triangles, but it was kind of like if we would have to redesign our entire workflow to avoid that problem. So it was just sort of seen as an acceptable loss. Because what we had was everyone was just doing so well at adding more and more content in by putting these boxes down, reorganizing the chunks, and also culling. We rolled our own custom culling solution, which also was just bounding boxes. And if the camera was inside a bounding box, the bounding box would say, oh, you can see these other culling sectors. And the culling sectors would have geometry as their child objects. So those chunks would be child objects of culling sectors. Not all of the culling sectors had those, because you could, as you go through a door, you might have a different set of geometry that you only want to see while you're going through the door. So in the animation, you can see as we get close to one of the doors, we get to see a bunch of the other rooms that we wouldn't from if we were inside one of those rooms proper. So we had these concepts of trigger ones and geometry ones, but it was really just a simple rolled solution of, is the camera inside this box? Cool, this is what it can see. And it's look, honestly, I'm not recommending everyone go and make a system like this, because we built this for the scale of our game, and it definitely will get out of hand if you're trying to do this on a larger game. But this is the kind of thing, like build bespoke solutions for what your game is about and what your game's restrictions are, because previously I'd used a much more complex system called Sector, which does really good portal-based environments. However, it's too computationally, like it just costs too much CPU to do the same job as this. So in this project, we rolled our own. And yeah, we accidentally turned putting more detail into the game into a game. And we got really good at it. And we got enough automatic processes into this system so that people were focused on making content, and they weren't focused on doing all the technical tasks to make the content work. The occlusion culling system was a bit shit, but like it could have been so much easier to use, but at the same time it met our requirements for, it was relatively easy to set up, it was easy to know when it did things wrong, and it fit the needs of the project, which was minimum CPU time possible. And the biggest thing was those benchmark limits we had, because we kept keeping them up to date, everyone on the team was able to help with optimization, and that's the only reason this game got done. Because otherwise, if there was only one person who knew what the game could do, testing every single one of the levels and fixing it up after someone else made a change, there's no way. That person becomes immediately a human bottleneck on the entire project's ability to get finished. And the game took long enough as is. So the final thing is the build pipeline, and you're probably going, oh, hang on a second, this is a performance talk. Why is there a build pipeline in this thing? Well, it's about testing on device and getting your team to test on device, because we were making a VR game and we did not have enough headsets. So we wanted people to use the headsets as much as they possibly could, get that iteration time down, but also get them to work on the device as much as possible. So the first rule is press play to test anything. An empty scene should run, an empty scene with a character in it should run. Put a player start position in there, the player should spawn. This is an example of me building like a minimum gameplay level where I put a player start position down, a floor, and 3 people for you to eat. And yeah, that's all. It just works. Any systems needed by the game should just be auto-constructed. The best way to put this is, I really feel that the Unity scene editor is a level editor, and it should be treated as such. You shouldn't be building complex architectures of systems that your designers can accidentally trip over. And that thing really means that, so this was the key, because this let the designers and artists just drop things in and test them. If someone wanted to test if a particular model looked right, they could drop it in. Now the second part of this is build and run any scene, one button, and no faffing about with the build settings window, because people can change that thing around for one test and then accidentally check it in, and all of a sudden everything's going wrong. So, and also building and running a full build on device is just too damn slow. And you've then got to run through the game to get to the location you want. There's everything wrong with it. So we rolled I've been maintaining a fork of UBS, which is an open source Unity build manager, but honestly, it's kind of like, it's an overkill solution. Just as long as you've got the ability to press one button and build and run at the current scene on any device, that's all you need. Just basically having it so that you're only building the subset of game you're testing. You don't have the full build time. You don't have to worry about getting to it. It just it encourages people to use the device so much more. And because of that, we actually had people testing for performance on the actual phone. We also had the problem that we wanted to support non-VR builds because we didn't have enough headsets to go around. So we had this concept of having SKU types or platforms. The way we did it was based around the fact that we already had a build manager. So we had a couple of editor scripts which we tied into this, which we essentially had you picked a platform, and changing platform would run the editor script that essentially moved or enabled or disabled the plugins for it. The other thing that platforms did was they injected a prefab into every single scene when you pressed play or when it built. And that let us get around the problem of having very different camera rigs for different kinds of things, like having a single point camera rig for non-VR and then an Oculus specific camera rig. And then also we had a Vive one which was supported as well for a while in development because we had 2 Vives just sitting around, which gave us a couple more people, like headsets for artists. So this was that's a complex explanation for a very simple problem. Basically just make it so that people can test in various ways, however it works for you. So yeah, Unity generally has a really good iteration time during prototyping. You press play and it does the thing. You need to work really hard to keep that. And that's what this build pipeline part of the talk has really been about. It's been fine during development. Everything you add to the game is going to chip away at that iteration time and make it worse and worse. And you've really got to work hard to keep it for the sake of everyone on your team. In our case, we had to build like single level builds, non-VR builds, and do a lot of work around that. But we managed to keep iteration time down, and we managed to keep people enthusiastic about using device builds and headsets. So that was it sounds really strange to say that this was a major contributing factor to having really good performance, but it meant that everyone was testing their stuff on device, which meant that no one was checking in content that wasn't fit for the device. So it saved time and it saved performance probably more than any kind of low-level optimization we could have added to the game. And that's the main part of the talk. The funny thing is I prepared a talk about 4 hours long trying to make this, so there are like 30 more slides over here. So if anyone's got any questions, I might actually have slides about them. But yeah, just open the floor. If you've got any questions at all, just throw them at me. Oh, there's one back there.
Can we grab these slides from somewhere?
Yes, they're online. You can actually view them and run through them. It's slides.com/CrateSmith/perf, P-E-R-F. All right?
Will you be tweeting that out?
Yes, yeah, absolutely. Yep. I'll come to you afterwards. Yes, sir.
Where's a good place to start learning how to write some of these sort of more complicated tools?
That's a good question. I would say look at have you got a copy of ProBuilder or a copy of any of these large tools? Because they come in full source code. So you can open them up and see how they've done all their stuff. And ProBuilder is a really good example for a really extensive tool that digs all the way through Unity. But there are much simpler examples, like having a look at the way that Cinemachine's been written. If you see another plugin do something and think, oh, I could attach part of my workflow to something the way they've done it there, chances are they've provided the source code and you can see how they've done it. And that's how I learn, and it's a really good way. It's basically like modding for tools design. Sorry, yeah?
That's okay. Can you explain what boxing is?
Boxing. Okay. Boxing is a problem in C# that happens when you have a value type, like a struct, an int, or a bool, and it's being passed to something that's expecting an object type, like an interface or an object, like the general word object. Like, so for instance, string.format, the function, it receives an array of objects. So if you go and string.format and pass an int as in as one of its parameters. Well, it has to get turned into an object on the heap. It can't be a value type because the value types only exist in the stack memory, which is the function stack, well, basically the call stack. So what happens is, under the hood, when it compiles this out, there's a special instruction that is box this. And what it does, it creates a temporary object in the heap that just contains that value. And it creates it, uses it, and then after that call's done, it instantly destroys it. And the problem with that is that every single operation that causes boxing has just added a tiny fragment-heavy object into the heap. So the garbage collector's got to do it. And big objects are easy for the garbage collector to clean up. But thousands and thousands of little tiny boxed ones, it's got to go through and delete every single one of those when it does a collect pass. So, and the really nasty thing is, you don't realize that there's no new keyword or anything like that. In fact, the only way you can really know for sure that there's no boxing is to go and open up, look at the disassembly for your code. So I've got a really nice thing that I do where I write code in Visual Studio. There's a plugin called Resharper, which I use, but it's one of its sister products, .peak, has got a window that they can put on the side, which actually shows you the disassembly of the current code you're writing, line by line. And you can just look through that and say, did this create any boxing? And you can see if it uses the boxing instruction. But yeah, the boxing rules are really important because they're invisible garbage collection instructions that you might not even realize you've done. And that's why link is really good in principle, but because of the way link works, it is so prone to doing these without you knowing about it. So that's why I say you can only use link if you've actually checked the disassembly, because you can't be certain that any link operation hasn't done something nasty. Anyone else? Nope. Okay, cool. Feel free to catch me outside. I guess this is probably going to go on there.